Yeah, you're recording.
All right, it's my first attempt. You might notice how I'm dressed, and I'm getting paid to dress this way, which is great. This is BC Calculus 2015, question number 4. Let me put BC here so I know later on when I look at it. All right, so part A on this question, you should have already tried this. So you're looking at me doing this in case you've realized you're a horrible person and you can't do this and you need my help. Awesome. All right, so part A, we have dy dx equals 2x minus y, and they want us to graph the slope fields. So I'm looking at the 5 ordered pairs, going to write them down. So my first ordered pair here is 0, 1. I'm plugging that in for the x and the y to find the slope. So 2 times 0 minus 1 is negative 1. So I go to this place and I make a slope of about negative 1. All right, second ordered pair is 0, 2. So I plug that in, 0 and 2, and I get a slope of negative 2. So here I get a steeper slope. It's a negative, but steeper. Next one I'm going to use is 1, 1. When I plug in 1, 1, I get a slope of 1. Now I'm going to plug in the ordered pair 1, 2. And I get a slope of 0. Now I'm going to plug in the ordered pair 0, negative 1. I get a slope of 1. And lastly, I'm going to plug in negative 1, negative 1. Whoa. Positive 1, negative 1. And I get a slope of 3. Quick warning, I have no clue if any of these are right. Awesome. So you can check online and make sure it's right. But I feel good about it, and that's important, I guess. All right, I think that's all the dots. Great, so that's part A. There's your points. And let's go to part B. Part B says, find the second derivative in terms of x and y, determine the concavity of the solution curves for the given differential equation in quadrant 2. Determine the concavity of all solutions. Okay, so one thing about quadrant 2, just really quickly, so in quadrant 2, the x coordinates are always negative and the y coordinates are always positive. We're going to need that at the very end of this question. Okay, so we first need the second derivative. Now this is second derivative using implicit differentiation. So when I go to take the derivative of 2x is 2, the derivative of y is 1, but we get the chain dy dx. And very importantly, this dy dx is replaced with this. Notice the question says, find the second derivative in terms of x and y. This doesn't count as in terms of x and y. We have to plug this in. And if I just put the 2x minus y here, I've made a big mistake. The obvious mistake here is this better be in parentheses. So let's make sure that looks right. Derivative of 2x is 2, the derivative of y is dy dx. Dy dx is replaced with this. All right, now I'm going to finish by distributing this negative to both. That's going to make this first one negative, and the second one is now positive. All right. So now I'm going to look at what happens in quadrant 2. So in quadrant 2, I'm replacing every x with a negative and every y with a positive just to see what happens. So this is replaced with a negative number, this is replaced with a positive number, and you'll notice 2 is now positive, a negative 2 times a negative is now positive, this is a positive. If you add all those up, you get a positive. So another way of saying this is in quadrant 2, the second derivative is always greater than 0. Therefore, those little 3 dots mean therefore. Therefore, concave up. All right, part C. Does f of x, let y equals f of x be the particular solution with the initial condition of f of 2 equals 3? Does f have a relative minimum, maximum, or neither? Now I haven't done this question, but before I do this, I'm going to go ahead and erase. If you're fast forwarding through this, you're probably missing the best part.
Do you want me to turn off the video when you're erasing?
Oh, no.
Okay.
Listen, they have to listen to my bull crap all the time. They love it. Oh, look how great it's erasing. This is going to be so much fun. Lydia, do you want to be a part of the video? You can walk out right now.
I didn't know you were done yet.
Yeah, nobody knows.
Okay, I'm
Well,
sorry.
all right, great. Okay, so here's the thing. If you're going to have a minimum or a maximum or neither, slope has to be 0. Slope has to be 0. So what I would do to check first is I would go ahead and plug into here the ordered pair. And they want me to check out the ordered pair 2, 3 to see is the slope 0. So I put a 2 and a 3 and I get 1. Now remember, this is the slope. If my slope is 1, that means my slope is not 0. So since this is not equal to 0, it is neither a minimum or a maximum. Now, what if it had been 0? If it had, it's not. This is it. Answer's neither, you're done. But if it had been 0, you would go to the second derivative test. If the second derivative would have been positive, so second derivative positive, remember that would mean concave up, where the slope is 0, it'd be a minimum. This is the second derivative test. If the second derivative would have been less than 0, it'd be concave down where the slope was 0, and you'd have a max. And if the second derivative and the first derivative both equal 0, then we would have a situation like this where it's a point of inflection. But none of that happens. All right, last question looks really weird. Again, I didn't look these up, so if this ends up being wrong, I apologize, but it says find the values of the constants m and b for which y equals mx plus b is the solution to the differential equation. Now, this is not a problem that you can separate and integrate. You can't do it. So, basically, it's a little bit of a sneaky question. The idea is that if you separate and integrate for some specific initial condition, you will get this, a line, as basically your original equation. Now think of it this way. If this is my answer, if my answer is a line, then the slope of the tangent line, remember that's the derivative. The derivative, which gives the slope of the tangent line, the slope of the tangent line will actually be the slope of the line itself. So this is where things get a little sneaky. If this was my answer, then my derivative, dy dx, the derivative of all this would be m. And this m has to equal this information way over here. So the m would have to equal 2x minus y. Now, why is that important? Well, if the m has to equal 2x minus y, I should be able to go back here and replace the m with 2x minus y. I hope this goes somewhere because it's not looking like it's going anywhere fun. Y equals, let me distribute, 2x squared minus xy plus b. I know I'm on the right track, and that got me absolutely nowhere. This is where I could look out into the classroom and say, Morgan, What am I missing here? I'm missing something obvious. All right, I'm missing one thing. I don't know what that one thing is. So I'm going to stop here, and I bet I at least earned a point. If you look up somebody else's video, I'm sure they would know how to finish, and I might know how to finish later on, but I do not now. So I'm going to go turn this off, or hope that I do, and we're done.
Let me get it for you.
What do you do to turn off?
Right here.